Hello, I'm Yuan Tian. Together with my colleagues in Azure Data, we're excited to share our progress in building autonomous data services on Azure. Modern cloud has transformed data services into commodities. Today, Azure, Microsoft's public cloud offering, provides a large range of data services to customers. Although benefiting from the economy of scale, cloud brings in complexity. For cloud providers, it's more and more challenging to manage every aspect of an expanding range of data services while meeting customer SLA and reducing costs. On the other hand, cloud users struggle to optimize their use of data services due to the numerous configurations and performance options to choose from. So, automating data services is a necessary outcome of the cloud. While cloud brings in complexity, it also brings in opportunity. Never before do we have such incredible observability of detailed workload traces and system telemetries collected across millions of users and applications. The expansive range of services and customer base allows amortizing the cost of investments in data science and machine learning-based solutions. Moreover, cloud makes it possible to roll out new updates at an incredible fast pace, often totally oblivious to the end users. Together with the recent advancement in data science and machine learning, it creates a perfect timing for using the data-driven approach to automate many aspects of data services, or building so-called autonomous data services. The authors of this paper are a group of data scientists, research scientists, and engineers from the Gray Systems Lab and Azure Data Product teams. We operate at the crossroads of research and product development, with a track record of delivering autonomous features for Azure data services. Our efforts have resulted in an estimated annual cost saving of $96 million for Azure. In this talk, I'll share our collective perspectives towards building autonomous data services. There are three layers in the cloud stack for a data service. The cloud infrastructure layer provides the hardware and software resources. The query engine layer delivers all the data processing capabilities. The service layer interfaces with users, allowing them to configure and tune a data service. All layers of the cloud stack, along with the interplay among these layers, need to be considered when building autonomous data services. And the goal of autonomy is to deliver simpler, faster, and cheaper services to users while respecting privacy. Now I'm going to showcase some progress we have made in this area. Let's start with the cloud infrastructure layer. Configuration tuning at the infrastructure layer requires collecting a huge amount of data points from combinations of varying system tunables. Here, sampling efficiency is the key. In some scenarios, existing telemetry data is sufficient for model training, but in others, additional data points are needed. However, collecting such data by conducting rounds of experiments on the production cloud infrastructure is infeasible. We can either devise clever ways to reduce the number of experiments or resort to emulating the dynamic system behaviors using ML based on domain knowledge and collected system metrics. Here's an example project called Kia, where we use domain knowledge and system metrics to emulate the system behaviors on Cosmos, which is an internal big data cloud service in Microsoft. Cosmos has different generations of machines with different skills. There is an important system parameter that controls the maximum number of containers that can run on each SKU. To compute optimal value per SKU type, we formulated as an LP problem, a linear programming problem, which maximized the total number of containers in the whole system subject to resource limitation and no worse overall performance than existing settings. In order to solve the LP problem, we need data points for what-if scenarios. Instead of running expensive experiments to collect the data, we built multiple linear models per SKU type to predict machine behaviors. The predicted data points are then fed into the LP solver. Now this figure shows the resulting suggestions from Kia compared to the existing settings. These optimal settings have been fully deployed on Cosmos. and generated roughly 18 million cost savings per year. Now let's move on to the query engine layer. The general principle of all our work in this layer is learning from the past to improve the future. This is based on our observation from real production workloads that queries or jobs are often recurrent and similar. Decades of research and development have been invested in improving various components of the query engine. So when we apply new data-driven approach to production-level query engines, we try to make as minimal change as possible. We use ML only when it makes a difference. Let's take a look at an example called Queue Advisor, which steers the optimizer for better plans using rule hints on the Scope Big Data Engine. We applied and adapted the state-of-art research ideas in BAO to Scope. This was the original Scope engine architecture. Over the years, through several efforts on applying ML to improve query optimization, the Scope team has added two major extensions. One is the flighting service that can be used to do A/B testing, for example, trying different query plans. And the other is the Stats and Insights service, where the Scope optimizer can call out external services like a Queue Advisor in this case. It turns out applying BAO to Scope is not straightforward at all. We need to make important adjustments. The original BAO work considers only 48 rule configurations for Postgres, but in Scope, there are 2 to the power of 256 rule configurations. To reduce the search space, we employ a contextual bandits model and restricted the steering to only one incremental step at a time. This not only simplifies the problem, but also provides better explainability and debuggability. We also introduced the validation step that utilizes the flighting service to run the query with and without recommended rule configuration. This validation model is our guardrail for regression. This work is deployed in Scope, and it is impacting 5% of the recurring jobs and saving 10 to 15% of PN hours. Now let's look at the service layer. In this layer, we use data science and machine learning tools to automate the customer-facing decisions by learning the profiles of customers. Models can be built with different granularities. At the coarsest granularity, we can build global models that are broad but may not be accurate. At the other end of the spectrum, individual model per customer will provide more accuracy, but requires sufficient data observations. This may also result in many models to manage. We need to find a middle ground. Often, we can group similar customers and applications into segments and build segment models, which transfers the learning among similar customers within the group. When there's not enough data to build individual models, we can start with a global model or a segment model and fine-tune the model for individual customers as we collect more and more data. Here's an example project called Doppler, which automates the skill recommendation for customers migrating from on-prem SQL Server to the cloud. By collecting data from on-prem usage on CPU, RAM, data size, and IOPS, and combining with skill configurations and billing cost, Doppler produces a price performance model that captures the trade-off between system performance and cost for a customer. Each dot represents a skill, and the value represents a percentage of the time that this skill satisfies the customer usage. As you go to higher skill, the percentage will increase, but it will also become more costly. The question is, with this price performance curve, what skill should be a particular customer choose? It turns out to be that different customers have different preferences on each dimension. Some customers might be more negotiable on CPU, IOPS, but not on memory, and vice versa. The second component of Doppler is to leverage the data on the existing migrated Azure SQL customers to build a customer profiler by segment analysis. Each group of the customers will share a similar negotiability profile. When a new customer comes in, we match the customer to an existing segment, then use the average sweet spot of that segment to give a final recommendation. The work has already been deployed as part of the Data Migration Assistant tool. Now I want to share some key lessons that we have learned. The first lesson is that simplicity rules. The common pattern across all our work is that simple heuristics tend to overrule ML, and simple ML models like linear models and tree-based models tend to overrule complex deep neural networks. The simplicity really helps manage the cost, scalability, debuggability, and explainability that the production engineers really care about. The second lesson is one size does not fit all. This is the micromodel versus micromodel arguments. A happy middle ground can often be achieved by a segment model or fine-tuning a global or segment model to individual customers. The third lesson is that sampling efficiency is the key. When observational data is not enough, we have to find clever ways to limit the experimental runs, or we use ML together with domain knowledge to emulate the system behavior. The last lesson is feedback loop is absolutely necessary in production setting to adapt to changes and avoid regression. Now I'm going to discuss some of the future directions. Over the years, we came to the realization that common usable solutions across different data services are highly desirable. So can we reach the holy grail of the reusable ML solutions? Although we don't have a complete answer, we are trying to tackling this problem at different granularities. At the function level, we're proposing an algorithm store where the previous developed functions and algorithm can be discovered and adapted to address new scenarios quickly. The next is component level reuse. Can we have a common infrastructure to support auto-scaling for all services or query optimization for all data engines? We have made some progress on engine-agnostic workload representation, characterization, and the feedback mechanism. At the highest level of granularity, all ML for system projects require system for ML support. System for ML is another big area of investment in Azure data. Standardization comes hand in hand with reusable infrastructure. We are working on standardization on telemetry, workload representation, cross-language query plan specification, and ML model representation. So far in our projects, we have primarily focused on optimizing individual components of the system. However, optimizing each component separately may not achieve the overall optimal performance. Ongoing efforts are being made to jointly optimize selected components and coordinate their deployment. Lastly, we have a responsibility to ensure that customers, big or small, do not get marginalized from autonomous decisions. For all ML-related projects, we conduct a comprehensive responsible AI assessment, which currently involves a manual and time-consuming process. We are working on improving tools to simplify this process. In this talk, I've described our experiences, the lessons learned, and some future directions towards building autonomous data services. However, many challenges remain to be overcome. We welcome other researchers to join us in this exciting journey. Thank you.